Today I would like to talk about electrical conductivity. So we're going to try and measure the electrical conductivity of this little aluminium ring. So to measure the electrical conductivity, we've got a really big electrical conductivity measuring device which sees how far we can fling it. So this is a big metal coil which could draw 100 amps if we could let it. And so what we do is we switch this on. It will produce a massive current going around it. As the current builds up, this will produce a magnetic field, and this magnetic field will send currents going around this disc. The currents going around this disc will make another magnetic field, which will oppose the two of them, and then just like when you stick two bar magnets together, they'll fling apart. And so this should go shooting down the lab, and we'll see how far it shoots, and that will tell us how well it's conducting. So I'm just plugging it in and checking that I've not done anything wrong. Good. So when we flick the switch, it will go bang! Go bang! It's gone. Where's it gone? Here we go. Right, so it went as far as the gloves. Right, so next we're going to see if we can make this fly further, try and get it much more conducting so we get a bigger current. I have to replace the fuse each time because this wants to draw 100 amps, these fuses blow at 13 amps, and we use the fuses to stop the whole thing setting on fire. There we go. Not the fastest reloading cannon. Of course, not the most powerful one either. So the plan now is to try and increase the conductivity. So if you cool something down, it will get more conducting. So here we've got a dewar of liquid nitrogen. So we dip that down into here. It's boiling away. I don't know if you can see it boiling away. Right, this should go a bit further. So this is on, this is ready, that's steaming, and boom! And boom! Right, so down the lab, don't run in a lab. We managed to hit the back of the wall. Oh, that's cold. So it went the whole way to the back of the lab. First time we shot it, it went from the cannon, one desk, two desks to the glove. And we've gone 1, 2, 3, 4, 5 and a bit, whole way into the wall. So that's moved over twice as far. So the piece of metal is made of lots of different atoms. So the atoms are arranged in a lattice, which is nice and periodic. But when it's at room temperature, which is quite hot, it's moving around all the time. There's lots of vibrations going through. So it's shaking around all over the place. The two are vibrating towards each other. And when it's nice and cool, this is vibrating much less. So the current that we're trying to put through it is made of lots of electrons. And electrons can move through the lattice if it's nice and periodic. Because of quantum mechanics, they're waves. They like to move through things which are nicely arranged. But if you've got the atoms vibrating and moving towards each other, it's suddenly not periodic anymore. It comes across, the sound wave, the atoms vibrating, will come in and they'll knock it off. So what you really want when you get a current going is an electric field which pulls all the atoms going this way really quickly. But if you've got the temperature, everything sloshing around, electrons will be battered off and you won't get the same kind of build-up of current. So the first time we did it, this was jostling around a lot. So the electrons tried to get through, they were being scattered off. And so the actual current going through it was not very much, and so it only went a little way. If we cool it down with the liquid nitrogen, it gets nice and cold. It's only moving a tiny bit. It's only moving a tiny bit, so as the electrons try and go through, less of them are scattered because there's less vibrations in the crystal. If less of them are scattered, more electrons shoot through. The more electrons shooting through, the further it flies.